So let's look at some exceptions to the octet rule. So odd electron species are otherwise known as radicals, and so these are species where it's impossible to pair all the electrons. And the classic example is something like nitric oxide, NO, and nitrogen is in group 5 and oxygen is in group 6. So you got 11 electrons, so it's impossible to pair these suckers up. So I'm going to go ahead and draw a skeleton structure and draw a line between, so that's going to leave us with 9 electrons. And I'm going to assign the oxygen to be the outside atom, so I'm going to go ahead and complete its octet by giving it 6 electrons. So that gives me 3 left. And then normally they go in pairs, but of course you can't pair one thing, so that last thing would go off by itself. So I've run out of electrons here. And again, I want to try and get my atoms to be as close to an octet as I can. So this nitrogen is not looking good. This oxygen's got an octet, but this nitrogen's got 1, 2, 3, 4, 5. So I can give it another couple, right? So I can go ahead and I can borrow those two and turn it into a double bond. That gives me 7 electrons and 8 electrons. And that's as good as I can get, actually, because if I take another pair of electrons and give it to nitrogen, which I could do, that would put nitrogen over at 9. And just like blackjack, right, you can't get a score above 21, you go bust. So you can't get more than 8 electrons here, so you go bust. So this is as good as it gets. And in actual fact, if you want to calculate formal charges, you should see that both of these have a formal charge of 0, which indicates that's probably the best structure you can do. A couple more exceptions here. We will find that boron and beryllium are often exceptions to the octet rule. We'll see that boron often only is happy when it has 6 electrons, and beryllium often only happy when it has 4. In fact, we can take a structure like beryllium dihydride, BeH2, and we can draw out a Lewis structure for it. I think beryllium is what, in group 2, and hydrogen's in group 1, and there's 2 of them, so that gives you 4 valence electrons. And so we can actually see there's only one way to use those 4 electrons up, and that is as so. And that is actually a perfectly valid Lewis structure. And we can do the same thing for boron. So boron actually forms a very famous set of compounds called boranes. They are BH3, and boron is in group 3, and hydrogen is in group 1. So we can go ahead and we can say we got 6 valence electrons there. Boron in the center, hydrogen on the outside, and that is as good as it gets, actually. You cannot draw a better Lewis structure than that. And you might say, well, that's kind of a cheat, isn't it? Because you can't really go any better than that anyway. But let's go ahead and take a case of, say, beryllium difluoride, and we could go ahead and try and draw a Lewis structure for this one. So beryllium's 2, fluorine 7 apiece. That gives you a total of 16 electrons, if I can count. We put the beryllium, oh my gosh, what is that, right? That is not a Be, right? We put the beryllium in the center. We put the fluorines on the outside. That uses up 4 electrons. Gives you a total of 12. We complete the octets on the fluorines. So there's 6. There's 6. And apologies for using the equal signs incorrectly there, math teacher. So that means I'm out of electrons. And you might say, well, that is done, right? Well, up to now, right, we would have said, oh, no, that's not done, right? You got to have an octet around the center atom, right? You got to go ahead and take those lone pairs, right? And you got to go ahead and share them and turn it into a double bond. So presumably, right, you can complete the octet by just sharing those lone pairs and looking at something like so. And it turns out that we know this is wrong for a couple of reasons. One is that experimentally, the bonds are single. Okay, well, that's kind of a big tell. It's got to be the bottom structure there, not the top one. But also, we can calculate the formal charges, and we will see that the fluorine has a formal charge of +1, and the beryllium has a formal charge of -2. And if we ask ourselves, does that look crazy? That looks very crazy, because fluorine is the most electronegative atom there is. To give it a positive charge, to basically steal electrons away from it, is not going to happen. Beryllium is not very electronegative at all. Its electronegativity is like 1.5, so it is really not going to want to take electrons away from fluorine and pick up a negative charge. So experimentally, we should probably say, since the bonds are closer in length to a single bond, that's probably the right structure. But if we didn't know that, we would look at these formal charges and we would say, hey, that looks pretty crazy, doesn't it?